Let's now get into parametric methods. So let's talk about parametric estimation. By parametric estimation, we are looking at a dataset X, which is made of n samples, which are xt from t equal to 1 to n. And we assume that each of these xt samples is following a given distribution given by px. Here for the presentation this week, we will work with 1D sample. So all the x's are scalars, are single variables. We will consider the multidimensional samples with many measurements, so vectors, next week. So first, we assume that this data set is made of independent and identically distributed variables, which we call IID. That means that these variables are following the same distribution. What we see here, that is the P of X, the likelihood Px. So this is the distribution function for the xt. And we assume that there are no relations. So we are building a set here, but the order is not important, for example. So we don't have some kind of dependence between the samples. So we get this x2 given that we have the x1. No, we assume that they are independent and they are following the same distribution. So these data are IID. So from that, we can basically make what we call parametric estimation. So we could define the Px here that we have, that is defining the distribution as in fact a family of probability density functions. So we have the Px given the theta. And so the theta is basically the sufficient density statistics. This is, I would say, you can state that as a way to estimate the parameterization of our model, of our distribution of the data. So if we are looking, for example, at a normal distribution, so we are notating the normal distribution here by this, which is basically a normal distribution of mean mu and a standard deviation sigma, a variance of sigma square. Basically, the theta is equivalent to these two parameters, so the mu and the sigma. With this, we are describing the density of the x, so the px given theta, for example. And so the point is to estimate this theta from a set big X. So our big X set is here, that is defined that way. We want to use it to estimate the theta that is corresponding to the parameterization of our densities describing the data. How can we do this? We will first look at the likelihood of an estimate. So this basically boils down to say what is the likelihood of getting a data set big X. So it's like, I would say, the likelihood for one sample, but for the complete data set. So how likely is it to get that data set? And so that likelihood is defined as the likelihood of getting the data set, assuming a parameterization theta. So we have this theta here, which is a parameterization of our model, and we want to look at the likelihood of getting this data set if we have this theta. And this can be simply described given that we have given that the samples are IID, so they are independent, identically distributed. We can simply state that this corresponds to the product of our individual likelihood. So the likelihood of the individual samples, x1, x2, up to xn. So this is what we are looking for. So we have this likelihood given the parameterization theta. And so we are multiplying this likelihood for each sample. This gives us the joint likelihood, the likelihood over the complete data set. We are going even beyond this because we will define what we call the log likelihood, which is basically the likelihood that we saw before, but adding a log before. So we have the big L, the big log, so the log likelihood of a given parameterization theta, assuming a data set X, which is equivalent to the log of the likelihood we saw before. And so we remember that log A times B is equal to log A plus log B. So this is a basic identity. From that, we can convert the product, you know, at the previous slide, this is a product. Basically, we just say px1 times px2 times px3. We will convert this product as a sum, given the log identity. And so it was down to the sum of t equal to 1 up to n of the log of the likelihood of getting xt given theta. So like I said, we have the log A times B is equal to log A plus log B. And we also have the log A power n is equal to n log A. So the log is interesting for that, converting a product into a sum. And it is also interesting to simplify the equations for some densities. For example, with a normal distribution, we have an exponential. So the log will cancel the exponential. So it will allow us to simplify some of the equation when we will have to manipulate it. And the good thing with a log is that it is not changing the order. You know, when A is bigger than B, in such case, log A will be bigger than log B also. So it is not, it is monotonic transformation. It is not changing the order of values. And from that, why are we passing through a likelihood and a log likelihood function? Is that we are using this to figure out what is the theta, what is the parameterization of our model corresponding to our data set. So we will look at the theta value that is maximizing the likelihood or the log likelihood according to our data set. So this is stated here. So we have the log likelihood here. So given the data set at n, so we have a data set, this is our data. We are assuming that this is, for example, following a normal distribution. It can be something else, but let's just say, for example, that our data is normally distributed. Then we can estimate the parameters of our distribution, in our example, the normal distribution, by figuring out the theta, the parameterization that is maximizing the log likelihood. And this will give us the optimal, the best theta to use, which are the most likely theta corresponding to our data. For example, if we are looking at Bernoulli's law, so we know that this law is simply to state that probability of getting x is equivalent to small p. So small p is the parameter of that law. So this is the probability of our distribution. So it's p power x times 1 minus p power 1 minus x. So this seems to be fancy, but in fact it's super simple because x is either 0 or 1. So when x is equal to 0, what we know is that the something power of 0, like here, is equal to 1. So 1 times 1 minus p at power 1 minus 0, it's power 1. So basically, for x equals 0, this is equivalent to 1 minus p. Conversely, when x is equal to 1, then this thing is like p power 1. So basically, it's p. And that part is 1 minus 1 in terms of the power, the exponent. So it's power of 0. So it boils down to 1. So we get back to p. So we would get that for x is equal to 1, the p of x is equal to p. And for x is equal to 0, the p of x is equal to 1 minus p. So it's a fancy formulation for something quite simple. But this fancy formulation is useful when we want to develop the equations, to develop, for example, the way to figuring out the value of p here, the parameterization to use according to our data set. So then we will first determine what is the log likelihood function of Bernoulli's law. This is that function. So we say the likelihood of parameter p of our Bernoulli's law according to our data set x is equivalent to putting a log. So we have a log and we are getting the product over all data set, all samples. So we have the samples from t equal to 1 to n. So we have the samples 1, 2, 3 up to n. And this is basically Bernoulli's law for sample xt. And we are making a product of this from 1 to n. Applying the log over a product, it gives us the summation. So we have a summation here. We are summing from 1 to n. And then we are using the other property like log a power n is equivalent to n log a. So this is how we get this from that here. So we have a product of pxt. So we have xt log p. And for the left part, it's the same thing. Basically, we are taking this exponent and we are having this here. Given that we are summing from 1 to n, we are summing the 1 n times. This gives us the n here. And we are making minus xt here. So we are minus summation from t equal to 1 to n of xt is here. All this log 1 minus p here. So we are converting basically this equation using the log identities to that equation with using summations instead of products. And from that, we want to get the maximum likelihood estimate. And how can we get the maximum of such function? This function can be simply, we just can simply get the derivative of that function according to p, and getting this derivative equal to 0. So we take this equation, we compute the derivative according to p. I'll let you do that on your own, but it gave us, when we are making this equal to 0, that we have a p hat. So we are isolating the p here according to the derivative, and it will give us something like the estimation of p, the maximum likelihood estimate of p is equivalent to the sum of xt here divided by n, the total number of samples. And if you look at this, it makes sense because it's basically what we said before about tossing a coin. When we are tossing a coin, we are looking at the number of tails divided by the total number of tosses. So the number of tails, the number of times where it is equal to 1, it is that thing. And the number of tosses is equal to n. So we are getting the same function basically, but having a more formal way to develop it, which is the maximum likelihood estimate of that function. We get into another example, which is the categorical law. So basically, it is the generalization of Bernoulli to k mutual exclusive states. So we can say basically k different classes. So then we have, I would say, as a state, x1 up to xk. So we have the variables x1, so which is basically in 0, 1, and we are summing this to 1. Basically, it gives us that we have a measurement, some kind of measurement that is a vector or a set of k values, but only one of these k values has a 1 and all the others has a 0. We also call this a 0, 1 odd vector. So each variable xi has a probability pi, but over this we have the summation of pi is equal to 1. So we can say that we are parametrizing this law according to 1 pi for each xi, and we are constraining this to be to sum to 1. So we can say that we have a state probability. So we have what is the probability of getting one given vector. So we have a vector of 1, 1, and all zeros elsewhere for k values. This corresponds to the product of the p I xi from I equal to 1 to k. So this is the probability of getting one given state. And then we are making independent experiments. So we have n of these states, n of these samples, basically. So we have this xt here. And so this xt is x1, x2 up to xn. And each of these xt is made of k values. This is the one odd vector. And basically that gives us, I would say, category. We say, okay, for sample one is category 3. So it will mean that the state X will be 0, 0, 1, 0, 0, 0. For example, in state sample 2, maybe from category 1, it will be 1, 0, 0, 0, and so on. So it's a way to represent something that is coming from one category among several categories, among key categories. From that, we can again apply the maximum likelihood estimate, which is similar to what we have before with Bernoulli's law, but we are making the partial derivatives of that maximum, that log likelihood function, making this equal to 0. So we have then k different functions, k different partial derivatives. And if we are isolating the variables here, we get something like pi hat is equivalent to the summation of xit divided by n. So this is giving us the estimate of the pi hat for all k categories that we are dealing with. Another example is with the normal Gaussian distribution. So if we have a Gaussian distribution, we assume that the distribution is parameterized by a mean u and a standard deviation sigma. So in 1D, this is that thing. So we are dealing in 1D only with 1D distributions today, basically, except for the categorical one. Here we have a px, which is equal to 1 divided by square of 2 pi times sigma. This is that part here, exponent minus x minus mu power of 2 divided by 2 sigma square. And this for the domain is between minus infinity and plus infinity. So this is the classical equation for normal distribution, Gaussian distribution. You should have seen this before several times. Then if we say that we have a set of samples, a sampling here which is made of n distinct samples, which are ID, and if we assume that these samples are following a normal distribution parameterized by a mu and a sigma, but we don't really know this mu and sigma, we want to estimate it from the samples, then we will use the log likelihood equation. So we just apply the log likelihood over this. So we are making the product of the px here given this normal law, and we are doing the log of the product of px here. With some developments, we are simplifying this to that part. So we have minus n over 2 log 2 pi. So this is basically that part of the equation. This is here. Then we have minus n log sigma, which is basically that part here. And then we have this thing, which is what we have in between brackets, because the log is canceling the exponential. So we keep this thing as it is, but we are making this as a sum from 1 to n. So we have the sum here that is done over that, divided by 2 sigma square, which is independent from the xt, so independent of t. So this is basically simplification of normal distribution inside the log likelihood function. And from that, we are making the partial derivative. So we will just compute the partial derivative of this log likelihood for mu and making this equal to 0. So this is one thing. We want to find the mu that is maximizing the likelihood here. So we get the partial derivative equal to 0. And also the partial derivative of sigma equal to 0. And we just kind of get these two equations. We are isolating from that what we call m and s squared. So m here is basically the estimate of mu, and s is the estimate of sigma. We are using Latin letters as estimates for the corresponding Greek letters. So the Latin is equivalent to mu is m, the Latin equivalent to sigma is s here. So the estimate of mu is summation of xt divided by n. So it's kind of standard way to compute the mean. but with maximum likelihood, we fall back on that. And here we have the maximum likelihood for the standard deviation squared, so the variance, which is the sum of xt minus m squared divided by n. Some will remember well their stats. We'll say, well, usually we divide by n minus 1, so n minus 1 here. Yes, this is the case for unbiased estimation of the standard deviation, but maximum likelihood doesn't give us that. It gives us divided by n directly. So we have a biased estimator, which is not perfect, but this is what we've got from that. In fact, if we are looking at the bias of an estimator, we can say, okay, we are looking to estimate the parameter theta with x. So we want to get that estimate. That estimate, we will call this d here. The d of x is the estimate of theta with x. And then we can get the quality of the estimate of d by evaluating the difference, the square difference between the estimate and the real value. So if we are able to get the real theta, we know that the real theta is that, and then we are estimating the version from the data set x. The difference is the quality is the difference of this squared. And so we can get into something that we call the quality of estimator d. That is the expectation over all possible samples. Let's say that we are able to, a data set is basically a sample. If we are looking at all possible data sets that we can get, and we are looking at the expectation of the quality, we get something like this. So we say that we are able to evaluate d over all possible sample of x. And from that, we can get what's called the bias of the estimator. So we say, okay, the quality is R here, and the bias is something like the expectation over all data sets of the estimation. So we have the expectation of the estimation compared to the real value. So if we have what we call a non-biased estimator, we see that b theta d is equal to 0. It means that the expectation over all data sets of our estimation should be equivalent to the real theta values. Okay, maybe it's kind of a big step here. We talk about expectations. So to get back on what you saw before in your probability and statistics course, we call expectation of a continuous variable x having a density f. This is defined like this. So we are looking at the integration of x times fx of x dx. So this is the integration over the domain. And this will give us the expectation of that variable. We can use then the transfer theorem for measurable functions gx. So this states that the expectation of gx here, this is the difference with what we have before, is then equivalent to the integral of gx fxx dx. So applying the transfer theorem, we get that, such that we can say that for a constant a, which correspond to a gx function equal to a times x, so the expectation of constant a times x here is equivalent, going through the formulation of an expectation as integral of ax fx dx. So a is constant, is not a function of x. We can just get this out, and this corresponds basically to a times expectation of x. And if we are summing two functions, if we see that gx is in fact mx plus nx, we can state that the expectation of mx plus nx, passing through the integral formulation, we get something like this here. And this here then can be decomposed. If we're integrating m plus n, we just have to integrate m, and we can integrate n here. So this corresponds to basically the expectation of mx plus the expectation of nx. So from that, we can develop further our equation. So if we assume that the samples have a density of mean mu, And M is a so we can say that M is a non-biased estimator of mu, simply by giving that, okay, we have the expectation over all data sets of M. We know that we find M as the summation of xt divided by n, something that we got just before. So this estimator of mu in a normal Gaussian distribution, we can get the 1 over n out of that. So we have the summation for all t's of expectation of xt. Given that the xt's are IID, they are independent, we can assume that basically we are summing the same thing n times. So we are summing, just wait a minute. So we have this thing here that corresponds to that. And this thing here, we are summing n times the same thing, because the expectation of xt is the same for all xt's, which is mu. So with that, we are just canceling the n here, and we have as, I would say, expectation of m equal to mu. And this means that we have a non-biased estimation. If we are looking at the variance of the estimator, so the variance of m over the x's, so we have something like the variance of summation for xt divided by n here. So we have 1 over n squared, summation of the variance of xt. So we have n sigma squared divided by n squared. And then we just see that sigma squared divided by n is equivalent to the variance of the estimator. So the variance of our estimator is equivalent to the variance divided by the number of samples that we have. So more samples we have, better is the estimation m. To get this, remind that variance is basically the expectation of x minus expectation of x squared. And so this is the expectation of x squared minus expectation of x squared. So we get this from that. And so we can say that it is an efficient estimator, because with a high value of n, with n tending to infinity, we have a variance equal to 0. And it is also a convergent estimator, because with the limit of n going to infinity of m is equivalent to sigma directly. So this is basically supported by the strong law of large numbers. Then if we look at the bias of the estimator S squared, we have a standard deviation sigma for a normal distribution. So we have this as, I would say, the standard deviation of our normal distribution. So the maximum likelihood estimation of sigma square, which is a square, which we defined before as equivalent to that, which is also the same thing than this. From that, we can get this quality of the estimator. We know that the expectation of if of xt squared is equivalent to sigma square mu square. So these developments are left on the side for you if you want to look at this further. And same thing, the expectation of m square is equivalent to sigma square n plus mu square. So this is basically, you know, this part corresponds to that. That part corresponds to that here. So if we put it all together, we get something like this. And going further simplification, we get into that thing. So this is where we've got our expectation of S square is equivalent to n minus 1 over n sigma square. And this is not equivalent to sigma square. That means something. That means that the estimator S square is biased. So we don't, it is not unbiased. It means that we will not get exactly the right value overall. We get something that is slightly biased by this. So it is slightly off what we would expect. So that estimator will tend to get us a slightly lowest standard deviation that what it should be. That's why we are in fact, dividing in when we get an unbiased estimation by n-1 instead of n, because by dividing by n-1, we will get into an unbiased case.